Myself, Dr. K. Viswanath, Allamraju, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to study about double integration method and solve some of the problems in double integration method. In the last session, we have covered the double integration method applied for a simply supported beam, and the point load is acting in the middle of the beam. So for that, what is the slope? The maximum deflection occurs at the midpoint. Yc is maximum at the center, and the slope is maximum at A and B at end supports. That is theta A and it is theta B. Now for that case study, we have derived the problems. We have derived the formula for that case study. The case study of simply supported beam having a point load at the center or concentrated load at the center. Okay, here the problem is that a beam of 6 meters long, simply supported at its ends, is carrying a point load of 50 kilonewtons at its center. The moment of inertia of the beam is given as 78 into 10 power 6 millimeter per 4. If for the modulus of elasticity of the material of the beam is 2.1 into 10 power 5 Newton per square millimeter. Calculate the deflection at the center of the beam and the slope at the supports. So deflection at the center of the beam, that means the maximum deflection. At the center of the beam, the maximum deflection occurs. And the slope at the supports is the maximum slope. Where the deflection is maximum, the slope is here, in this case, it is 0. The slope at the center becomes 0. And the slope is maximum at supports A and at support B, that is theta A and theta B. So here the theta support at A, theta A equal to and theta B, and the maximum deflection occurs. Here one more thing is that this is a case study. If you draw the free body diagram or data to be based on the data, if you draw a diagram, it is similar to the point load. It is acting at its center. Yes, it is related to the case study of a simpler supported beam subject to a concentrated load at the center of the beam. So here a beam is 6 meters long, is simply supported at its ends. It carries a point load of 50 kilonewtons. Carries a point load of 50 kilonewtons at the center. The moment of inertia of the beam, that is I section here, that is 78 into 10 power 6 millimeter per 4. And modulus of elasticity of the material is 2.1 into 10 power 5 Newton per square millimeter. So if we consider it's the point A and it is the point B and it is the point C. So point C, the maximum deflection occurs here at the center, that is Yc. They draw a tangent to your supports, that is theta A. And if you draw a tangent to the radius of deflection curve, that is theta B. This is the slope at the supports, theta A and theta B. The deflection at the center is Yc. Now span of the beam is 6 meters, that is 6 convert into millimeters, that is 6,000 millimeters. And the point load, that is 50 kilonewtons. 1 kilonewton equal to 1000 newtons, convert into newtons, that is 50,000 newtons. Now the formula derived for that case study here, it is the Yc, the maximum deflection at point C is WL cubed by 48 EN, where W 50,000 newtons, L 6,000 cube, 50,000, 6,000 cube, and 48 E 2.1 into 10 power 5, I 78 into 10 power 6. So after substituting those values in the formula, and the calculated value is 13.736 millimeters. This is the 13.736 millimeters. That means here it is 1.3736 centimeters. That is the first objective. And the deflection at the supports, A and B both are equal. The maximum, the slope at the supports A and B are equal. That is theta A and equal to theta B. That is downward direction. That is a negative slope. That is downward slope. That is WL square by 16 EI. We know the value of the W, that is 50,000 newtons, and L value 6,000 millimeters by 16 times E, 2.1 into 10 power 5, 2.1 times I value 78 into 10 power 6. So the observed value here, it is after substitution, it is calculated, and the value obtained is 0.06868 radians. Convert it to degrees. After conversion into the degrees, radians into degrees, for that conversion you have to multiply with 180 by pi degrees, 180 by pi. So after multiplying, the observed value in degrees is 3.935 degrees. That is theta A and theta B. That is slope at supports. Slope at supports theta A and theta B. Slope at supports, that is theta A and theta B, which is same as, that is 3.935 degree inclination. That means with the inclination of 3.935, the maximum deflection is observed here 1.3736 centimeter. That distance 1.3736 centimeters. For the slope at inclination, that is 3.935 degrees. So in that manner, we have to apply the derived formula of a simply supported beam subject to a concentrated load at the center, and the observed the maximum deflection at the center is WL3 by 48 EM, and the slope at the supports is negative of WL square by 16 EI. WL square by 16 EI. That is the slope. Units for slope is in radians or in degrees, and unit for deflection is in millimeters or meters. So let me see another problem, how to calculate for the same. So here, problem for a simply supported beam carries a point load at the center. Case study, you are going to see the problems. So problem is that a beam 4 meters long, a beam of 4 meters long, the span of the beam is 4 meters and simply supported at its ends, carries a point load W at its center. If the slope at the ends of the beam is not to exceed 1 degree, that is theta A, is point A, it is point B, and theta B. And theta A equal to theta B equal to 1 degree, that is 1 into pi by 180. It is in terms of radians 0.01745 radians. Now of the beam, find the deflection at the center of the beam. So we need to find out the deflection at the center of the beam. What is the deflection? YC, the center of the beam, it is at point C, maximum deflection. So how to calculate? We need to find out deflection, but the given input parameters are, so here the deflection, we have to find out deflection at the center of the beam. That means that is the maximum deflection, and the slope at the centers, that is theta A and theta B, given here it is 1 degrees, that is 1 times pi by 180, that is 0.01745 radians. So for the given data, the input parameters are span of the beam and the weight load at its center. It is in terms of W, we don't know the value. So let us find out. The W is not given, only span of the beam and slope are the input parameters are given, that is theta A and theta B. That is 2 input parameters, and W is the unknown. So but we have to find out the deflection at the center of the beam. So let us find out the given data, that is length or span of the between two supports is 4 meters. Converted into millimeter, 1 meter equal to 1000 millimeters. So 1 meter equal to 1000 millimeters, 1 kilonewton equal to 1000 newtons. Theta A equal to theta B equal to 1 degree. Convert into radians. To convert degrees to radians, you have to multiply it with pi by 180. So converted here 1 degree, 1 into pi by 180. The observed value here it is 0.01745 radians. So how to solve the problem? So let us, given that based on the data, that is slope. The slope at the ends of the beam is not to exceed 1 degree. That means by using the slope, we can connect it to the maximum deflection. The deflection is YC, that is WL by 48 EI. WL by 48 EI. So what to do? The slope can be make it WL square by into L in terms of that is 16 EI. So what happens 3 times, that is 3 times 16, 48. So this WL square by 16 EI is nothing but the slope at A or at supports, that is the theta L by 3. So we know the deflection theta A value, the theta A is value given here 0.01745 radians, and L convert into millimeters, that is 4000 millimeters by 3. Then we get it deflection at the center, even though the weight at the center is unknown. Weight at the center is unknown, but we can find out still the maximum deflection, provided the slope at the supports are known. Now W square by 16 AI equal to, that is 0.01745. Then go for deflection. So we know the equation. From equation, deflection is for the case of, this is the formula only for the case of a simply supported beam subjected to a point load at the center. At the center, the C is the center, A and B are the support. For this case study, for this case only, the deflection at the center C is WL by 48 EI, and theta A equal to theta B equal to WL square by 16 times EI. These are the two formulae are only applicable for the case of a simply supported beam subjected to a central concentrated load at the center. For that case study only applicable. Otherwise, you should not use these two formulae for other cases. Like if the load is acting eccentrically, that means not at the center. If the concentrated load is not at the center, either away towards left support or towards right support, but not at the center, then the formulas will be changed. Then we have to derive again for the deflection and slope at the supports. So those case studies we are going to study in the next sessions. But for this case study, we should be very specific, and this formula are applicable only for the case of a simply supported beam subjected to a concentrated load only at the center, and there is no other loads like uniformly distributed load and no uniformly varying load. It is at the center only considered only concentrated load. So for that, here it is the deflection at the center is the maximum deflection, and also at the center C, that is YC equal to WL by 48 EI. So we have to divide this WL by 48 EI into two terms. The term should be in terms of slope. So this is WL square by 16 EI, L into L square into L cube, 16 times 3, 48 EI. So the formula is remains same, but we divided into two parts such a way that this part is related to the slope. That is WL square by 16 EI is theta A or theta B. So WL square by 16 EI, that is into L by 3. Substitute in the place of WL square by 16 EI the value of slope at support A in terms of radians, or you can see the degrees. In terms of radians, you have to substitute that is 1 degree. Here the theta A and theta B slope are in terms of slope, in terms of radians, but not in degrees. Even though the data was given in terms of degrees, we have to convert that degrees into radians by multiplying into pi by 180. The value obtained in terms of radians of theta A and theta B, here it is 0.01745 times L value, that is 4000 millimeter by 3. So after it is obtained as 23.26 millimeters deflection, provided the slope at the support is 1 degree. The slope at the support is 1 degree. The slope at the support is 1 degree, that is theta A, that support A, and theta B, this is 1 degree. The deflection at the center YC equal to 23.26 millimeters. So after knowing this deflection, one thing is that we can find out how much weight it is subjected to, even though it is not asked. What is the procedure for this? We know that YC equal to WL cube by 48 times EI. One known value, there are two more unknowns are there. So yes, the 60 E and I value. Suppose if we know the material, if we know the section of section geometry of the beam, then we can find out the weight. What is the how much weight it is being acted on the beam. So the maximum deflection here it is 23.26 when theta A equal to 1 degree. Theta B is also called 1 degree, that is slope is 1 degree. Now coming to one more problem we are going to solve here. Let us find out. In this case, we have to find out the deflection again at the center of the beam. So let us read. Let me read. The beam of 3 meters long. A beam of 3 meters long is simply supported at its ends. Simply supported at its ends. Is carrying a point load W at the center. Is carrying a point load, that is W at the center. Okay, is carrying a point load W at the center. If the slope at the ends of the beam should not exceed 1 degree, should not exceed 1 degree. Okay, should not exceed 1 degree. So find the deflection at the center of the beam. Find the deflection at the center of the beam. Find the deflection at the center of the beam. It is similar to before problem, but it's very important to practice. Yeah, I think. But here the only difference is that in before problem, the span is 4000 millimeters. Here, remaining thing is the slope remains the same, that is 1 degree. But the span in the before problem that between two supports is 4 meters. Here it is 3 meters. So here it is 3 meters and 1 degree. Here it is 1 degree. Find the deflection at the center of the beam. So first, what type of case study here it is? It is a simply supported beam subjected to a point load at the center. We don't know unknown value W, but the length, the span between two supports is 3 meters, and theta A, suppose it supports at A and B, it is at the center. This theta A equal to 1 degree. At the same time, theta B, that is also theta A equal to theta B equal to 1 degree. So the slope should be in radians when we are going to solve the problem. So theta A and theta B converted 1 degree into radians, that is 1 into pi by 180, that is 0.01745 radians. And we have to find out the deflection at the center, that is the YC. So deflection at the center for this case is the maximum deflection. So we know the deflection at the center YC equal to WL cubed by 48 times EI. But we know the value of theta slope, that is theta A or theta B equal to WL square by 16 times EI. This WL square by this theta A value, that equal to 0.01745. So they convert, make it divide this deflection, the equation of deflection into two parts, such a way that one part related to the slope, another part is in terms of factor, in terms of parameters, that is in terms of span. So here WL square by 16 times EI by divided by multiplied by L by 3. This WL square by 16 EI is nothing but slope, at supports, that is YC. Theta A terms WL square by 16 EI is slope at the supports theta A times L by 3. What is theta A here? The theta A is already known, that is 0.1745. So 0.1745, this is theta A term. So 0.1745 times L, what is the L value here? The span between two supports, that is 3000 millimeters, 3000 by 3, that is 17.45 millimeters. So in the before problem, for this span, if we observe L versus deflection at the center and also slope theta A. So here, if we draw a table, theta A is remains constant. Theta A equal to 1 degree for both the cases. L is 4 meters and second case is 3 meters or 3000 millimeters. For 3000 millimeter, the deflection is 17.45 millimeters. Okay, we make it into 3000 millimeters. L in terms of millimeters. Or it is L in terms of millimeters, that is 4000 millimeters. And the value for the span of a simple support, that is for 4000, that is 23.26. So we can understand from these two cases that the deflection is maximum. Deflection is maximum for the maximum span between two supports, is proportional to L. So L value is increasing here, that is this 5.81 millimeters or more, 5.81 millimeters or more in comparison deflection value of a 4000 millimeters length of the beam in relation to the length of the beam is 3000 millimeters. So if the span is reduced, that is 3000 millimeters, then the value here it becomes how much here? That is 17.45 millimeters. But the slope at the supports remains the same, 1 degree. So from this relationship, from these values, we can understand the relationship between deflection versus length of the beam. If the length of the beam is more, the deflection becomes more, increases. If the length of the beam is small and deflection also decreases. So that means YC deflection at the center is proportional to L. So it is the linear variation. It varies linearly because the W is remains same, E is remains E, and modulus of velocity and section, provided this condition is suitable only when load and EI are same. That means section of the beam and material of the beam and load of the beam and theta is the same, then means what will happen? The slope remains the same. But if L varies, L varies, then the deflection also varies. So in proportional to the L variation of the L, deflection is varied. So it's the linear variation. That's what we can understand from this. So what is the units for W? Let me, we have to make it. What are the units? WL cube by 48 EI, where WL cube by 48 EI. Where W is the concentrated load in terms of in newtons, and L is the span of the beam in terms of millimeters. E is the modulus of elasticity or Young's modulus, it is Newton per square millimeter, and I is the area moment of inertia of the section of the beam, that is millimeter per 4. So if you substitute all these values, then the deflection of the beam is in terms of millimeters will be obtained. So when newtons, when WL cube by 48 EI for that case here, that is the Newton deflection units is in terms of millimeters. If L is in meters and modulus of elasticity is in terms of Newton per square meter and area moment of inertia is in terms of meters per 4, then the deflection comes value in terms of meters. So one should be one should pay attention in substituting the values for maintaining the dimensional homogeneity. If you are substituting in terms of meters, you have to substitute all values connected to meters, which should be in meters. Then the output value, the deflection value becomes in terms of meters. And if you are using vice versa, that means if L is in millimeters, E should be in terms of millimeters, that is Newton per square millimeter, I in terms of millimeter per 4, then the deflection becomes millimeters. So in that manner, we have to we have to substitute the values. Otherwise, the value becomes definitely goes in wrong direction. So these are the problems we solved in this session. So what is the double integration method? Especially I already used the terminology double integration method. So we use the equation obtained, that is m equal to EI into d square by dx square. We know the basic equation, m equal to EI times d square y by dx square. This m is the moment at any section. If it is simply supported beam subjected to concentrated load at the center, then we write the momentum equation, bending moment equation. Then what will happen? If we derive this equation d square by dx square, if we integrate once, it becomes dy by dx. This dy by dx is nothing but slope. And integrate the slope equation again, then we'll obtain y, that is the deflection. So that's why that means double integration method. If you integrate twice the equation, that's the momentum equation, then you'll get it. First integration gives the slope value, and if you integrate again the slope equation, we can observe the deflection. So in that manner, here the slope equations, that's why the name derived for here, it is double integration method. So in this session, what we have done is mainly we concentrated on how to apply the derived formulae by using double integration method, especially for the case of a simply supported beam subjected to a concentrated load at its center. So it's the pure. For that case study, we solved the problems and used those derived formulae to obtain the deflection values and the slope values. So the deflection is maximum at the supports. Deflection is maximum at the center where the concentrated load is acting. And the slope is maximum at the supports. So what happens to the slope at the support? The slope at the supports are 0. And the slope at the center, deflection is maximum, is 0. Slope is 0. Theta c equal to 0 at the center. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.